I really want to, like, once you graduate, like, you get to have like an alumni card, like a star or like,
Ask Ben.
right?
Ben can totally accept that.
We deserve it. We work hard.
Yeah. It would just be cute. Senior staff.
You know, to see someone who wants to, like, guys, how does the register work? Or how does the diesel flop? And we're just like,
Alright guys, let's start our lecture for the day. So this was an internal lecture that two engineers from my company put together, me, Kiran. He's a distribution operations engineer. Took the same class, was my capstone partner. We ended up working in the same company. So this day in, day out job is power quality, and both of us worked together to put together sort of a 3-day class for our technicians. So this is just a snippet. It's got way too many slides. This is day one. I believe it's like 50 slides, but I am showing only 10 or 15 of those slides. Because the more slides I show, the more I have to talk about stuff that's sort of not relevant to this class. But if you end up taking masters, there is a power stability class that you have to take. I think you have to take, in which we cover everything. Anything and everything that should have been part of this presentation. So first, let's just take a quick look at, we already looked at what harmonics are. Sorry? So now I'm heading into a new topic called harmonic distortion. That's where we start. So harmonic distortion happens when, and this is very important, when a non-linear load draws current from a power system. And I'll show you a bunch of examples for a non-linear load, but keep in mind, it has to be a non-linear load to create a harmonic distortion. The current is drawn in short pulses and not entirely during the voltage waveform. And the non-linear loads draw non-sinusoidal current. And I believe in your homework, there is a non-sinusoidal problem that you have. But keep in mind, for the time being, just understand the current would be non-sinusoidal, and that introduces a distortion to the current waveform. And if the distortion is pretty high enough, it will eventually create havoc in the voltage also. For the purpose of this class, 95% of the time, we are just going to deal with current distortion. We will talk briefly about the voltage distortion, but we will assume it to be 0. But just at the offhand, don't be alarmed if you see voltage distortion as well. These are some of the components that can introduce harmonics, like a rectifier, arc furnace, adjustable speed drive, SCR, SMPS. This is more to help the technicians visualize, not for you guys, but you know, you have a voltage. The current you expect is sinusoidal. It may be phase shifted, but it's still sinusoidal, and you have a linear load. In case of a non-linear load, you have a voltage, and the current is non-sinusoidal. There is a bit of, not a bit, there's a whole lot of notching and whatnot in the sinusoidal. So just to give you an idea of what a linear load looks like and what a non-linear, just because it's a lighting device doesn't mean it has to be linear or non-linear, depends on the device. Depends on the device. Similarly for the motors, if you have just an induction motor, it's a sort of a linear load. The moment you have a drive introduced, it's a non-linear load. Again, that's part of 348 and your machines class, which is a 500 level class. But it gives you a great visualization what I'm talking about, a linear and a non-linear. And of course, Neil wanted to point out again, because technicians might have slept at this point, that hey, electronic balance, arc furnaces, SMPS, which is your typical brick that you use for your laptops and whatnot. They are all non-linear loads. And if I look a bit uninteresting because this is like, man, this is not what I want at the 300 level, and I'll soon get to it. In fact, the next slide after this is what I really want you to look at. So again, depending on waveform shows the difference between linear and non-linear. I mean, if you look at the current, it should immediately pop up to you that it's a linear or a non-linear. Current and voltage look similar. I covered this. Yeah, this I just wanted to put it once more that non-linear loads create a current distortion, and which then creates a voltage distortion. What I'm trying to say this is from a utilities perspective, because we don't create a voltage distortion. We want you to have sine wave, but it's at the end what you put as a load is your business, and that can create a current distortion and thereby affecting our voltages. All right. I typically don't show you graphs without head or tail, but there was some customer info that I had to pull out. So what this is showing you is, here's a sine wave of a voltage, but without any load. What we were trying to show is, hey, this is my voltage, and because there was really no load at the other end, the current is almost like a zero thing. And it's on the A channel showing that it's the A phase that I'm measuring. Quickly, can you guys tell me what this 277 is all about? Thank you.
Yeah.
So 277 is the phase. Again, you really pull the A phase here, so it should be the 277. And I'm assuming RMS at this point is okay with you guys? That this is the RMS voltage? We then put a load here, and if you can see that the current is actually just has a phase shift. It's still sinusoidal. I didn't know that it picks up whether it's Y or delta connected. Okay. And immediately when you put the load, the current draw actually increases and it's 75 amps. You may or may not notice this. We do a trick where we supply a bit higher, so that when you stick a load, you get your 277 for a linear load. In fact, it's 277.2. We change this throughout the day depending on what's happening. But, yeah. And this is literally from a customer. Our ask was to supply 277, and once you have, and we were supplying 277, what happens is current distortion started to take place, and that messes up our voltage distortion. Anyone wants to take a guess what that load would be?
Maybe the line of VFDs, like 20 of them. I don't know.
Could it be a motor?
Could be a motor, yeah. So same deal. I believe here we just started to add more drives. Yeah. The more drives we added, the more waveforms became distorted. At this point, it's hard to. There's no real data coming in. We are like telling the customer, hey man, we need to do something. There's no point calling us. Sorry, no point in keeping on calling us and trying to solve your issue. We need to figure out what's happening. So how do you calculate harmonic distortion? It's calculated in percentage. What happens is, at every frequency there would be a certain current that you get, and I'll walk you through. I'll complete the derivation that we started last week, and that should tell you what these currents are. So for the time being, assume you have a bunch of currents that are coming in. So it's just not your fundamental. So your X1 is your fundamental. X2 is at 120 Hertz. Current or voltage, it could be either. For the purpose of this class, again, I'm reiterating that we focus only on current harmonics. So X THT and X is just general. It could be either the kth voltage or the kth current. This is your primary or a fundamental current or voltage. These are your 120 hertz, 180 hertz, all the way up to 50 hertz. 50 hertz is where IEEE 519 asks us to stop. Most days, 20th harmonic, 25 is where we stop. So this should give you a percentage, and similar to your power factor, where we said a power factor of 1 is always nice, but you can never actually get it. Anything above 0.9 is great. Similarly, we come up with different percentages. And I think I have a slide for, oh yeah, I do. So total demand distortion, I don't think it's part of, I doubt if it's part of your homework. If it is there, it's more or less the same as, in which case you are going to look at the demand current. Now we haven't talked about max demand current, so I'm not expecting this on the exam. But I just wanted you to have an understanding of maximum harmonic current distortion in terms of percentage of the line current. These numbers, this tell you number of harmonics that I'm considering. So less than 11 harmonics, between 11 and 17, between 11 and 23, 23 and 35 and 35. So around 35, that's all that I'm doing. I don't think TDD is part of your syllabus at this point, so, but in any case, I just wanted you to have this.
Can you show the last slide again? Thank you.
So if you have a perfect, and this is just going more of the same, so if you have a perfect sine wave, you only have one harmonic, which is your fundamental. If you have a symmetrical waveform, there would only be odd harmonics present. The even ones cancel out due to symmetry. Now, this is a bummer, and I still wanted to have it here. Depending on the textbook, they will still tell you the even ones will cancel due to symmetry. That is true only for 3-phase. So at your home, where you have a 120 and a 240 coming in, this is not true. But when we are training up our technicians, we are dealing with 3-phase power, industrial loads, and that's the only reason that it was there. I put this in red. Some of you might be interested, but not part of this class, like a 6-pulse drive. And if you have 0 harmonics, which means it's just a DC voltage, like there is no distortion to it. So triplet harmonics. I do have a derivation, and probably I'll do a class example which will let you know why we need the triplets. So if you remember from the last lecture, we had even and odd frequencies happening. Even were at 120, 240, etc. Odds were happening at 180. So the third harmonic, fifth harmonic, seventh harmonic, ninth, etc. And I'll walk you through the derivation today. But turns out you need to be bothered if you are in the 3-phase system, not in a 2-phase. If you are in a 3-phase system, you need to be bothered only by the 3rd, 9th, and 15th. And you keep on going. What this means is you pick all of your odd harmonics, and then you decide of the odd harmonics which one are multiples of 3. Let me just walk you through that. And the only reason I'm doing this in a scattered way, I know I'll give the derivations. What I found during the first 2 lectures is, gave you the derivation. There were certain points that I called out multiple times, and when I looked through the chat, I'm like, yeah, I mean, it's the same. So I'm just going to give you the highlights and then walk you through the derivation. Okay. So this is my harmonics. The first one is what? 60 Hertz. The second one was 120. The third was 180. Thank you. Fourth is 240. Nice. Fifth is 300. Sixth is 360. And sorry guys, this might look a bit easy, but at the same time, this causes a lot of issues. This is 420, 480, right? And 540. So for the purpose of harmonics, and that too for just for a three-phase, keep that in mind. These are the ones that are going to cause you an issue. 3, 6, 9, and then of course 15. That's again going to cause 15 is
900.
Is it 900?
Yeah.
Okay.
Not 3, 6, 9, not 12?
Not 12, and the reason for that is what you need to do is 3 times n, or 3 times I took h, right? Let's do 3h. You keep in mind that it has to be 3 times an h. So, and it has to be an odd number.
I think so. 6
It's not
is no.
6.
Oh,
Yeah.
that's sorry. No 6.
Okay.
3, 9, 15, no 12. So if I put the other way to look at it is 3 times 1, 2, 3. Put any number for h. And if you get an odd number, yeah, you need to pick that up. 3 times 3, 6, not required. 3 times 3, 9, required. 3 times 4, 12, not required. This is how I did it, because, but this is how you will find it in the text. So 15 is required. So what this is telling you is 3 times h, where h is your harmonics, 1, 2, 3, 4, 5, 6. Let's do 3 times 9, which is 27. So what this is telling me is my first harmonic, which being the fundamental, is needed, but it's not, the third, the 9th, the 15th, the 27th harmonic is going to be important, and it's going to cause some sort of an issue. And these are called the triplets. So 3h, and then pick the odd number. So this is my triplet. So let me write that down for you. The third, say, no, come on. The third, the 9th, 15. I don't think I'm going to ask you more than this, but yeah.
21.
Do we get to 21? 3 8s are what? 3 7s are?
3, 7.
Yeah, so then 21,
Yeah.
yes. So again,
Hopefully we don't.
not most likely, this is where it sort of ends, but yeah, let's go with it. 21st, 27. These are called triplets. And most folks would tell you, yeah, triplets are the only ones that cause harmonics and create a lot of issue. Keep in mind that's only for 3-phase. The 2-phase system, it's a different scenario altogether, but I'll come to it.
Nice.
We haven't looked at the, okay, yeah. So triplets add up in the neutral, and what happens is if currents are adding up in the neutral, we began with a three-phase source and a load, and I showed you it's not necessary that you have a neutral, but always push your customers to have a neutral. And the reason is because of these harmonics. If you are running a three-phase system, do yourself a favor and always have a neutral. The reason is the triplets will add together and will show up in the neutral, thereby, and if you have current running through a conductor, it's going to create E. Also, you need to know how to size a neutral. Now, you already went through a homework where you sized the hot lines or the main lines. You need to figure out how to size the neutral, and I will show you through the derivation. In case we don't get to it, it should be 3 times your phase current. And why that is, I'll show it to you. I think that's much better. And triplets can really create a havoc in the transformers by causing something called a circulating current. Not a part of this lecture, but I might bring it up during, I believe it's starting next week when we have our transformers. This, I just threw it because you have I was under the impression that you were doing your lab 2 today, but it didn't happen. My understanding it's happening after several weeks now. In case you end up doing it, you will see this spectral analysis where you have certain amount of current for the 60 Hertz, then for the third, then for the 5th, 7th, 9th, 11th. And keep in mind this isn't a 3-phase, and that's the reason you are seeing the 5th harmonic and the 7th harmonic and whatnot. If this was a 3-phase system, even that I don't think is oh, that's just a 480 watt. If this was a 3-phase system, you would have seen a third, you would have seen a 9. Somewhere here you would have seen the 15, and you can see how the currents are dropping so much that it doesn't make much sense for me to ask you anything past 15. I put up 21st and 27th, it doesn't make any, there's not a whole lot of difference. And this is an actual voltage and current that we picked up. So a lot more slides, but for the purpose of this class, I think we can stop here for the slides. And then yes, no. So anyways, here what I'm trying to show you is we started off this topic, I believe we did up to the 3rd one and called it good the other day. I just went home and did a bunch of other harmonics as well just to bring in the idea. Again, this is for we are discussing a 3-phase system, just to be clear. So what I did is, my first harmonic, nothing new here. It's IA, IB, IC, and these are the three angles associated with it. 0, -120, and 120. At this point, is there any confusion with at least these angles? No. All right. I then put in my second frequency, which is how much? Would be 2 times 60 Hertz is what I'm trying to show here. And I end up with the 0 remains 0, the 2 becomes -240, 2 times 120 becomes 240, positive 240. And this, if I plot out -240, can you see how it became a positive 120, or do you guys want me to draw it out for you? Does it help? Don't care? All right.
If you could draw it out.
Hmm?
If you could draw it out, that'd be nice.
All right. We saw this during our second lecture where I drew an ABC and an ACB sequence. So this would be my ABC, where I have an A, I have a B at minus 120, and I have a C, which is at positive 120. Any questions on this? All right. Still at balance. Okay. Whereas I have an ACB, but I still keep my A as 0, my CA actually is at negative 120, and my B was here, and that's at positive 120. At the time, I didn't say too much about it because I was waiting for this lecture to come up, and initial idea was to make it part of your homework, but then with how things have been going, I decided to pull it off. I wanted to add an additional problem to do. So anyways, when you go with your IA2 and you get your 0, negative 240 and 240, keep in mind this, let's just look at this IB2, which is with negative 240. So this is 0. If I go this direction, this is minus 120. And if I go one more negative 120, I end up here. So what's happening is my B got swapped with C, and my C got swapped with B. Do you guys get it? So without doing a whole lot of wiring, what has happened is you guys went from an ABC sequence to an ACB sequence. This is a big deal if you are running a motor, especially. Motors depend on A, the right winding. So you have to connect A to A phase, B to B phase, and C to C phase. They also expect a rotating magnet to come in like, they expect the first A, then the B, and then the C. Look here what's happening. Just because there is harmonics, the motor is actually going to see ACB, and it might stall, it might jerk, it might overheat, all kinds of nonsense can happen. Fortunately, this ACB is again, when you do the numbers, it's sort of balanced because you have a 0, 120 and negative 120. Now going for the third harmonic, I do the same, 0, 3, negative 120, 3 times 120. And when I multiply 3 times negative 120, I end up with a 360 with a negative sign, which is a whole circle, if you can see that. In other words, you end up with 3 currents, all with 0 degrees and all with the same phase. And that's what I said. This current, the third harmonic, will show up on the neutral. And it would be the sum of IA3, IB3 and IC3. But it will show up as A magnitude, which would be same for all these 3 and with a 0 degree. So your I neutral in this case is 3 times IA3, IB3, IC3, or 3 times the phase current. And think of this, think about this. You designed a breaker 1.25 times, great deal. You put a conductor. You are assuming that your neutral is going to work, not really. The neutral is actually having 3 times the phase current. So be very careful, figure out what your loads are. It's not enough that you have a source. You also need to figure out how your loads are responding. Just going to jump ahead and just tell it to you guys. Because this is a frequency, the easiest way is what you have seen in your 200 level. Make a bandpass filter or some sort of a filter that will just take out multiples of, will take out the triplets, so to say. So you come up with a filter that takes care of the triplets. Triplets if it is a 3-phase, not 2-phase. Again, I'm going to repeat that. I did it for the 4th as well, and at this point, it feels like more of a troll than anything else. But at the same time, keep in mind, this again, I got it as ABC. Check it when you are doing your problems, whether you get an ABC or an ACB. I did it for the 5th as well, just to make sure that I'm getting the numbers right. And I got an ACB, but luckily it's all balanced, so to say, so it cancels itself out. you guys need to check, do the same for n is equal to 6, 7 and 8. I went ahead and did for n is equal to 9, and like I said, I just wanted to point out that there is triplets. Be careful that it is 3 times the triplet current and whatnot. So I did my IAN 9 times 0, 9 times negative 120, 9 times 120. I get these big angles, negative 1080, 1080. I think I subtracted 3 times 120 or probably, no, 3 times 360. And if you add or subtract 360, it doesn't matter. And thereby I got again zeros. So this tells me that the I neutral is 3 times the triplet current. So I jumped ahead and showed you what the triplets are. This is how I like to do it. I just write the 3's table, so to call. 3 times 1, 2, 6, 9, 12. And people get tripped, and that's the reason I would like you to focus on this and not this. Because to me, I know I don't have to worry about this part. After that, I'm all just looking at the odd numbers. So this is good, this is not good, this is good, this is not needed, this is needed, this is not needed, this is needed. So figure out either way. Textbooks go by 3 and odd. So you do 3 times your harmonics, first, second, third, and you just pick the odd ones from there. It's up to you. I just don't want to hear a lot of whining during the exam or during homework. Oh, I got confused by that. Told you. So just trying to be a bit obnoxious today because of the level of questions that were coming in. And yeah, I'll hold it for now. So we went through these 2. The next topic is an easy one. It's the easiest stuff that you can get on your homework and your midterms and for any exam, including your FE or PE if you're interested. We talked about power factor during our lecture 2, I guess, first week anyways. And we were always talking about power factor, and that power factor is the true power factor. Or rather, sorry, that power factor is mostly to do with displacement power factor. And the reason is we were always talking about the 60 Hertz harmonics. So this V1, I1 is the 60 Hertz voltage RMS and the I RMS. But now, as of today, we also know that there are other frequencies that come into play. So what's the new power factor that we're talking about? Turns out it's an easy math. This is again from IEEE 519, and I keep referring to IEEE 519 because it's a decent sized document, several hundred pages, but I don't want you to actually fret and start reading through it. We have picked up the main parts and we have just thrown it here. But if you have an interest, go ahead and read it. So once you have a distortion, you need to come up with something called a true power factor. So displacement power factor, we have already talked about it, and we need to come up with something called a distortion power factor. A few minutes ago, we looked at a total harmonic distortion. You get a certain percentage. All you have to do is take that percentage in percent, not in decimals, drop it here, divide by 100, and please, please, please don't forget the square. You will end up with a value which looks very cute, very nice, and it will throw you off the game. And trust me guys, if it's a multiple choice, that solution without the square is always a solution. And yeah, I'm stressing on this because I forgot in one of my exams and it was like, yeah. So anyways, true power factor, this guy is VRMS, IRMS, of all the frequencies. And how do you find an IRMS? You take all the currents, and you have seen this formula when you were doing your, was it wire gauge? Then you took the currents. Oh, you were trying to find the IRMS, yeah. So I1 square, I3 square, I5 square, I7 square. Keep in mind, I'm thinking of 3-phase. I think I wrote it somewhere. Oh yeah, for 3-phase. If you have a two-phase system, so to say, you'll have a 2, 4, 6, all these currents in show. And on an exam, if I give you I3, I1, I3, I5, I7, you will design your hot lines using this current because it needs hot lines taking all these currents. But if I ask you to design your neutral, you would avoid 1, you would avoid 5, you would avoid 7. Rather, you would take only your triplets. And again, this is 3-phase that I'm talking about. So 3, 9, etc. and you do that. And don't forget this 3. We just saw that it's 3 times that current. Again, it's something that I don't like to do, but I will end up doing is, if you just give me the triplet current square and expect me to give you full points on an I neutral, that ain't happening. 3 times the triplet current. So if you're designing a neutral, give me 3 times the triplet current, else it's not happening. And oh yeah, I just wrote the formula that's typically used, which is free and odd. Last but not least, if there is no distortion of a voltage or a current, then this value that I was talking about would be 0. Keep in mind, even if I put a 0, doesn't mean this power factor goes to a 0. It's 1 divided by 1 plus 0. So which means you'll end up here as 1 over 1, which is 1. So just because you see that there is no voltage distortion, don't get into a hurry and say, oh, power factor was 0, which is absolutely wrong. What happens when your total harmonic distortion is 0 is this entire term reduces to 1, and then you only have to find out this guy times this guy, and you end up with your power factor. Any questions on that? Did you guys take this down as part of your notes? You need it for your homework. You guys already have this notes from somewhere, or what's
No,
the
we
deal?
took a photo because I know I can't write that fast.
Okay. You guys all
Is this recorded? Or no?
no. After a lot of push and pulls, last week I brought my LinkedIn back to life. I'm trying to get out of all this, but my boss was on my case. He just wouldn't let me. I'm like, "Yeah, just leave me alone." So if you're thinking that I'm going to allow myself recorded on some device, yeah, good luck. Anyways, I don't think this was part of a lecture in the previous years, but I just wanted to bring it. And don't take it casually. The reason is, I was looking at your homeworks, and I saw that you have a 120, 240 volt, blah, 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 and look at the RMS currents given. N is equal to 1, 2, 3, 4, 5, 6, 7, 8. So even without me jumping and telling you, this is a 2-phase system. Similarly, but we didn't cover that. Yeah, we'll come to it. Okay. So for a 2-phase system, all right. We previously found that the triplets in 3-phase systems add if a neutral line is present, while all other harmonics are cancelled in the neutral. Now let's consider a 2-phase system, and this is exactly, and I believe Daniel Anischenko and I, first day we talked about it, but I kind of swallowed because I knew I had to come back and explain this. So, for a moment, you have 3 lines going next to your house, those big, not the big ones, but yeah, you guys get the point. The ones on which you see a lot of birds, not the ones which are like way down where no one actually gets. And I'm just going to make this up as A, B, C. between any two faces, you will get a 1247 kV. So between these two faces, you will get a 1247 kV. Goes without saying that if I put a multimeter between A and C, I'll get a 12.47 kV. Quick question. Keep saying multimeter and voltmeter. How do you measure these voltages? Have you seen a multimeter capable of
No, I don't know.
12,000 volts? No?
No, tell me about it.
Yeah, not today. I'm running
Oh,
out of
not
time.
that. Sounds cool.
But the way you do it is, I'll give you the 30,000 view. You will step it down, and we'll see what a step down is. Essentially, you're going to reduce this voltage. I think we reduce it to like 120 volt AC. And then we have equipment that can measure 120 volt AC. And then we just do a bunch of that. So what would be the line cut? So this is going across your street, and from there I'll take a tap, bring it to a transformer that looks like a can on a pole, and it's got a sort of a triangle here where it drops, and from here you will have a line coming, depending on your neighborhood. Old neighborhoods, it's just tapping from here and heading to your home directly. Newer neighborhoods, it's beneath the ground and then pops up in your house. But because I'm tapping it off a line, it's 12.47 kV divided by √3. So you end up with, I just remember it as 7.72 thousand volts, supposed to be right here. Oh yeah, 7.2 kV. So that's how you get the voltage to your home. Now, someone figured out, and I don't know who that is, but anyways, you have a 12.4 kV between the lines, and if it's just one line, 7.2 kV, doesn't matter. We do a transformation through some windings. They tapped off the middle of the winding, and that's how you're getting a 240 at home. So you have 120 here, 120 here, but if I stick a meter here, you will read 240. So 120 for most of your appliances, the other 120 for the other half, like upstairs, downstairs, depending on how you want to think of it. And then 240, if you have a dryer, for most dryers 240, and then there are some electric ovens that need 240, is my understanding. Mario, I had a quick question for you. Nuclear subs, do they use 600 volt?
No, it was 440.
It goes 440, okay. There is a new discussion about using 600 volts, and my bet is if that's becoming a thing, Middle East would be the first one to jump at it. It makes more sense. For some reason, they are so there's so much excess power there, but at the same time, they are trying to push the envelope. I recently understood they came up with a light. It's actually called Dubai light. Are you guys aware of a Dubai light? I thought it was just a fake meme and I had to look it up. So the government of UAE or Dubai, one of them, worked with Philips to come up with a light. It's nicknamed Dubai light. Pretty cool. We don't do that. We just ask you to do it and we'll give you $10.
Okay.
It's also illegal over here.
I'm sorry?
I'm pretty sure you can't like import them to sell them over here either.
I'm not even sure,
Yeah,
but
there-
I'm pretty sure I'm going to get one. You don't make nice things and you don't keep it. Yeah.
Is it Y like the, how do you spell that? Is it like the letter Y or?
Oh
I'm
my
gonna
god, the
Google it
things
later.
that I get myself into.
Well, you just
Give me a
tell
second.
I'll Google it later.
No, give me a second. Now that I've, shouldn't be. Is it Dubai night or Dubai night? Of course, I have no internet. Sorry guys, no internet.
They
So
heard
check
you.
it out, it's either Dubai light or Dubai lamp, that's the nickname. Look it up, read it. I found it actually in an IEEE magazine for crying out loud. But anyways, so now considering this system, you can see that there is an IA flowing through here and an IB, and I didn't show you here. This is my neutral. So I have an IA, and this is considering a linear load, which means it doesn't have an SMPS, it doesn't have an SCR. So all that I have is 60 hertz in both the cases. So my IA, I took it at 7 ampere and some frequency, 60 hertz. I took my IB, the same frequency, because hey, it's a linear load, so no harmonics. But I did a phase shift of 180 because the current is literally opposite of what IA. The direction is literally opposite of IA. So if this was going clockwise, this is going anti-clockwise. A bit of math juggling will show you that the neutral, in this case, with a fundamental frequency, the neutral current is 0. And that's because anytime you add 180 degrees to a cosine function, so cos of any theta plus 180 is negative cosine theta. So essentially what you end up getting is, and I didn't write it down fully, 7a cosine 60 hertz t minus 7a 2 pi 60 t. So these two actually subtract, and you end up with a 0. And I know I'm throwing a lot of cosines at this point, so please make sure that you have downloaded the FE reference book. And the two sections that I would like you guys to have a printout is from the math section, get a printout of the trig, and the electrical engineering is like just 15 pages or something. Just print out the entire electrical engineering. FE reference book, publication 10.3. This was the latest as of first week of April. I'm not sure if there's a new one.
Do you know where we could find it, or are you asking us to buy it for class?
So once you go to NCES website, you just need to do a simple registration, and I think it asks for your college. Give them a dumb home address, dumb phone number, and just download it. So next, let's just consider a non-linear load in a two-phase system. So the way I'm doing a non-linear load is, again, 60T, 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 but I'm adding a non-linear by adding a second harmonic. This is my first harmonic. If you can see 2 pi or omega t, 2 pi f. This is 2 times 2 pi f. So that's how I'm getting my 60 hertz here. And this is 3 times 60, so 180. And if you notice, this is your triplen. This 1.5 current is your triplen. Similarly, the 1.5 is your triplen here. Now we looked at the first harmonic, previous page, and we saw that adding the first two currents leads to a 0. So I'm going to focus here on the triplen and then come back to the second harmonic. So I do the same stuff with the triplen. My first triplen is 1.5 cos 3 times 60, so that's A. For my IB, I added a 180 degree to compensate for the fact that the currents are in the opposite direction. Again, when I go through this, keep in mind 3 times 180 is actually 360 plus 180, and we just saw that adding a 180 degree to a cosine is actually negative cos theta. So this current, which is your third harmonic from the A phase and the third harmonic from the B phase, actually cancel them out, and your triplen current for a two-phase is 0. Now we don't discuss this with our technicians because they don't need this, and I don't think anyone in their homes is actually running big SCRs or SMPS that our technicians need to know. But two-phase, keep in mind, it trips me whenever I see that. People just really start saying, hey, triplen, so make the neutral 3 times and all that. Keep in mind that's true for 3-phase, not true for 2-phase. For 2-phase, in fact, your triplens, even though we call them triplens, your neutral is 0, so which is very good. So I showed you 60 hertz, we just discussed 3 times 60, which is your third harmonic, 180 hertz. Now I'm going to show you the second harmonic, and by now probably the plot is clear. So I pick up my 4 ampere 2 times to get the 120 hertz, which is my second harmonic. 4 ampere 2 times 160 to get 120 hertz, and 180 to counter the fact that the A and B are in opposite directions. And again I end up with a situation where I get 2 times 180 degree, which is 360 degrees, which is equivalent to 0 degrees. So in your second harmonic, it's your second, sorry, in a 2-phase system, it's your second harmonic which adds up. So keep that in mind. So for the 2-phase system, even harmonics add in the neutral. So if I give you a mixture problem with a 2-phase system, and I ask you, hey, what's the neutral current? Don't pick the triplets, pick the even ones. So 4 ampere plus 4 ampere ends up giving you an 8 ampere cosine to 60 hertz. And then at this point, because keep in mind this, you are in a cosine, and we don't deal with cosines at all, like the final answer. To get the RMS, take this 8 ampere divide by root 2, you get a 5.7 ampere. Now I just went a step ahead and checked what the IA RMS was. That's coming from, remember the 3 currents that we had? So 7 ampere on 60 hertz, 5 amperes at 120, and 1.5 amps at 180 hertz. I did an RMS square, just to find what my RMS currents were. And for a 2-phase system, it's 5.8 amps. This is the reason at home, when you're looking at your neutrals, you might end up, you will end up sizing your phase and the neutral with the same cable or conductor. They may or may not know the physics or engineering behind it, but unknowingly all that you're doing is you figure out your phase, and because the way the connection is made, the neutral is more or less the same. I mean, 0.1 ampere, you're not going to change the conductor. So the big takeaway here is, here the neutral is handling as much current as the hot lines. Keep in mind, this is 2-phase that I'm talking about. 3-phase, it is 3 times the phase current. And rarely loads produce significant even harmonics. So at home, you can get away with it, but we still prefer to have a neutral. Not at home, especially when you have hotels and whatnot, we ask them to put a neutral.
Nice.
Now I have a class example, but before that I just want to show you a topic that stands out by itself. It's a very small topic about convergence. What the entirety of this convergence is, how many harmonics are you going to take? Like, where's the end game? IEEE 519, it's not a rule book, it's not a law. They tell you take up to the 50th harmonic. But as an engineer, at some point, there is a cost involved. You have to hire a power quality engineer. You have to have a substation engineer on the other end who has to read through his report. And if it's a PESU student, most likely in LaTeX, he has written it. Go back and give him comments, and he edits it. We go back and forth. There's a lot of cost involved. So at some point, we decide, okay, so much convergence is good enough for us. After that, I could care less. So what you do is you pick a particular harmonic, let's say harmonic number 21, and then you do an n minus 1, so harmonic number 20th, and you divide by harmonic number 21, you find the TSTN minus 1, and do this jazz and get a percentage. And typically we ask for 0.2, 0.1, that's good enough. Because after the 15th harmonic I showed you, like a current just dropped, there's no point in keeping on doing stuff. But from a homework perspective, I think you guys were asked for point. Yeah, do you remember? Oh yeah, there you go. So from the purpose of homework, we asked you for 0.2. And yeah, so that's the way you go about it. In other words, you have an IA current given to you, this is non-sinusoidal. You do from n to infinity. No way should you be doing n to infinity. Pick up a spreadsheet, build a nice spreadsheet, and start putting numbers. And the moment you reach around your convergence of 0.2, not around 0.2, you have to beat 0.2. So beat 0.2, and that should be the number of harmonics that you need.
Could we use a calculator like Desmos to do that?
Oh my God, don't start using a calculator. Like, you have to run this calculation several different times. So use a spreadsheet or MathCAD or some software, MATLAB. Yeah, I have a question. Yeah,
That's good.
Back to the last paper you did. What's the THD stand for again?
What stands for what? Sorry.
Total
How
harmonic
many terms
distribution.
to consider? This guy?
Oh,
Total harmonic distortion. So this guy,
Distortion.
THD, and I'm doing this for a 3-phase. You guys good?
Total harmonic distortion, I thought it was total harmonic distribution.
Distortion.
Distortion, thanks.
Yeah. And the solution to the problem is here. If you guys can find it, read it.
So with the triplets going over the neutral, is that something that we just deal with, or do we try and prevent that with filtering?
You try to prevent it by filtering, and there is a we throw a certain amount. We tack on certain dollar amount to your bill. Older customers who have like several-year-old devices, they'll rather take the fine than do anything about it. And we are kind of screwed because our neutral is heating up. Our transformers are getting burnt or getting overloaded. So we have to deal with it. And we have folks who know how to talk nicely and get them to agree to some sort of a payment plan where we put in half, they put in half, something.
Does it affect efficiency at all? Or is
Oh
it
yeah,
just
yeah.
good
Transformer
heat?
efficiencies are, oh my God. Circulating currents are a big deal, especially when there's a fault, it creates havoc.
My question goes back to the homework. The 0.2%.
Oh,
Is that as in less than 1%, like 0.2, or is it 0.2?
it's 0.2%, right?
It's 0. So
Yeah.
okay, I was just
So-
making sure I was reading it
So
correctly.
this is in
'cause
percentage, convergence is always given in percentage.
Okay, but on the homework question, it says 0.2%. We need to go that tiny?
Yeah.
Okay.
Why wouldn't we do it? Yes, 0.2%.
You said less than 0.2%?
So, if I ask you to be here at 6:40, it's either be at 6:40 or be at 6:39 or 6:35. Don't show up at 6:41. That's what
Yeah.
I'm trying to say.
Oh.
So 0.2%. If you hit the 0.2%, cool. I don't think you're going to hit it. So yeah, and do use a spreadsheet. Please don't try to do hand calculations. Talking from experience, I had the same homework back in the day. And if you have seen, I like to use a lot of pen and paper. Spend a lot of time. But, yeah. MathCAD, MATLAB, spreadsheet, whatever, and make it neat so that your grader is able to see it and he understands what's happening. Alright, so board 3 phase and board 2 phase. So the next is actually a class example. Do me a favor, take a 5-minute now and then come back. So let's meet at what?